And that now allows us to move forward to compound systems, because now I can use hinges to actually connect systems. And that's in fact what you saw already for the simply supported frame, the simply supported hinged frame, if you will. So let me actually start by talking about that one. So here's why that works. So the way it looked was something like that. And it really doesn't matter what the angle is or what the dimensions are. Conceptually speaking, the reason this system works is because, yeah, you have 1, 2, 3, 4 support reactions, but you also have another initial condition, which is the moment being equal to 0. And so you can, for example, take the sum of the moments about this point and set that equal to 0. And you can take the sum of the moments about that point and set that equal to 0. And so you actually end up with two equations with two unknowns because you have this boundary condition. And this applies to other systems as well. So compound systems, I'm going to leave room for another easy compound system up there. But for example, I could have another compound system, which let's say looks like this. I have one rigid beam on the left and another rigid beam on the right, and I connect them with a hinge. And this right now would not work. I need to support it. And let's say here on the right side, I put a cantilever support. But of course, you paid attention and you know that this hinge here allows rotation. So therefore, this system here would fall down now. And therefore, this part would currently be kinematic. What can I do to stop it from being kinematic? I can just support it anywhere. I just choose to do it at the end here right now. So I have one more support on there. And now if I count my support reactions, what do I have? I have 1, 2, 3 support reactions on the right side and 1 support reaction on the left side, gives me 4. But I also have that the moment at the hinge is equal to 0. And therefore, that is my initial condition or my boundary condition, which allows me to solve these 4 support reactions. This is true here as well. So let's write down that here I also have a hinge and I know that the moment at the hinge is equal to 0. So these are two kinds of statically determinate compound systems. And you now understand why they are statically determinate and also why they're compound systems. So they're statically determinate because you can still solve them with equilibrium, but you have compounded the systems. For example, here you have a cantilever beam that is connected to a simply supported beam. And you may think, how is this a simply supported beam? It's clearly missing support here, but that is not true. Why not? Because the cantilever here provides the support for the simply supported beam here. So this is a cantilever on the right side and is simply supported. And they are connected through a hinge. Like I said, there's other systems as well. Let's draw yet another one, like one complicated one, I guess. And let's say we have a hinge here and a hinge here. So I need my dashed line because it's always rigid bodies. And of course, I need support reactions as well. So let's say here I have a hinge and here I have a hinge. And I bring in a support, let's say here. And then I have a support reaction here and a support reaction here. And this now is a way more complicated system, but you can see that you can still solve them because you have two unknowns to the right side of this hinge and two unknowns to the right side of that hinge. And why is that important? Because, as you remember, m at hinge is equal to 0 and m at the hinge is equal to 0 here as well. So what you can do, conceptually speaking, is you can take the sum of the moments about this point and you can, for example, release this system here and find 1, 2 support reaction. That would give you one equation with two unknowns. And let's call that equation 1. But you can also have your equation 2 because you know that your moment there is equal to 0. And in this equation, you have the very same 1, 2 unknowns. And so you have two equations with two unknowns, which you then can solve. And you can find the answer. And once you have those solved, you could, for example, go ahead and take the sum of the moments about this point here and have a third equation. And then you would have a third unknown in here, and that would allow you to solve the system. Let's look at this system here in a similar fashion. How would we solve this? And to make it a little bit more relevant or easier to follow, let's actually add a force on it. So let's pretend that I, for example, have a force acting here on the system. Let's call this F1. Now, how would I solve the support reactions? Correct, you guessed it. You know that your moment at the hinge is equal to 0. So therefore you can create subsystems. You can create a right subsystem, which won't help you in this case much. But you can also create a left subsystem. So let me draw that. So let's say I do what I call a cut cloud. So I cut this system. I release this system from the structure. And now I know that my moment here is equal to 0. That means that everything in this cut cloud here has to balance at this point. So whatever F1 is causing in rotation here at this point has to be balanced by RAY. So let's add actually an RAY here. So let's call this RAY. And hopefully you can see that RAY times its distance to the hinge has to be in balance with F1 times its distance to the hinge. And this is true because here rotation is allowed. And so this left subsystem has to be in balance. And therefore I can solve this. But then the next confusion comes in. Let's say you now already know what you have. Let's say this here would be 10 Newton, for example. Then the students often are confused. What do I do with that information? There's a hinge here. How do I calculate these remaining support reactions? And the answer is, once you have this, you do not worry about the hinge anymore, because the entire system has to be in equilibrium as well. So RAY, F1, and everything else that would potentially act on the structure would have to be in equilibrium with the support reaction. So for example, if you were to take the sum of the forces in the y direction, then you know that you have an R, let's call this by here. So RBY plus RAY must be equal to F1, right? So this would be the equation for this entire system. And likewise, this moment here, MA, about the z-axis, so MA about the z-axis has to be in equilibrium with everything that acts to the left of the system. There's no exception to that. Again, I see students often initially being confused by the hinge here, but the trick is, once you've figured out one unknown, the hinge does not matter for now. At least as long as we talk about support reactions. Later on, when we talk about internal forces, of course it has an impact. But again, we'll talk more about that later. So for now, don't worry about this. You find your subsystems, you find the side that you can solve easier. So for example, the right subsystem here, you could have not solved that. So if I were to cut the system here and I call this here system 2, that is something I would have not wanted to solve initially. I would have want to solve subsystem 1. And once I have all my answers from subsystem 1, I can apply them to the entire system. So maybe for clarity, I should even add like a third system here. So that would look something like this. So I have a third system, and that also needs to be in equilibrium. So if I would have solved this type of structure, I would have first solved subsystem 1 and then system 3, if you will. And I kind of did the same thing over here, and depending on how the systems look like, of course the systems may be very different, so don't be fooled by just understanding one type of system. Every system is different, and my experience in the classroom is that if I change one length or one dimension, or I put the hinge somewhere else, sometimes students already get confused, but the concept is always the same. You try to break it down into subsystems that you can solve with the information that your moment is equal to 0 at the hinge, and then you apply it to the rest of the system. Now, last but not least, I told you that I left some space here for the last simplest compound system, so let's go ahead and draw that just for completion. There's one more system that is technically also a compound system. It's really not a difficult system, and it's called a simply supported beam with overhang, and that looks like this. So we have a support here and another support here. And now we have overhangs on both sides. So why are these compound systems? Because I have a simply supported beam and the overhang is technically a cantilever. And here in this case, I have it on both sides. So this would be called a simply supported beam with overhang. And so that's why it's called a compound system. But in conclusion, compound systems that are statically determinate are always systems that are made up from various different systems that are statically determinate in a sense. And so you can now identify these systems and you can, of course, understand why you can solve them. Which takes me to our last section here for the lecture today, which is statically indeterminate systems. So let's move on to statically indeterminate systems.